Here we have a Plimsoll lines built on the side of the ship, and this will help us to identify what are the areas where the ship goes. Could it be it's traveling near the fresh water or traveling near the seawater? And this has something to do with the weight of the ship itself. Okay, ship is really heavy, but it is also huge enough to displace a large amount of water. When it displaces a large amount of water, you know that from buoyant force equals to the weight of the liquid being displaced can be given by rho Vg. If you displace a large amount of volume of water, which is the red circle V, you can actually have a very large buoyant force. The large buoyant force is equals to the weight of the ship. But at the same time, ship is also a hollow body overall and less than the liquid beneath. Therefore, it floats. But we want to find out why in ocean water, sea water, and river water, fresh water, why is it they are different? Why they sink at different level? Looking at this one, we have sea level, seawater and fresh water. The density of seawater is 1003, the density of fresh water is 1000. But first thing first, the weight of the boat is the same for both circumstances. Then this boat is 2000 and it sinks less, indicated by the red portion, which is less. And then you look at this one, in fresh water it actually sinks more. Why does it sink more? But before we find out, we need to know that the upthrust supporting must be 2000 as well. For both, the upthrust supporting the boat must be 2000 as well to keep the boat floating. If the upthrust or buoyant force is not 2000, the boat will sink, continue to sink further. If the buoyant force is more than the ship itself, I guess the ship will actually jump out of the water. So to keep it float, the FB must support with 2000. So FB is the weight of the liquid being displaced, rho Vg. Okay, so this is the buoyant force is 2000. We must provide with 2000. And this one is 1300, density of seawater. And the volume needed is unknown. So we know that V can be found quite easily using this, 2/13. 2/13 is equals to 0.15. Okay, so it actually has a portion of 0.15 water being displaced. How about here? In fresh water, still you need to support the 2000 no matter what. Weight of the liquid being displaced, rho Vg. So your rho now is different because it's 1000. So V is different. We use prime and times 10. And you still have to support with 2000. So because of this, you can cut it off. You can get 2/10, which is 0.2. So comparing this and that, we realize that in fresh water, it displays more portion of water, which is indicated by the red portion here. It actually displays more volume. Why displays more volume? Because you need more buoyant force to support. Okay, you need more buoyant force. You need the same amount of buoyant force of 2000 to support the ship. But unfortunately, because the density of your water is less, it sinks more so that it can displace more volume of water so that it can provide more buoyant force. Okay, so this is the conclusion. So even in cold water and hot water, cold water is more dense, so it actually floats better than hot water. Okay, hot water is less dense, so it will sink more into the water. Hot water is less dense, the ship will actually sink more. So this kind of marking actually help the people in the ship industry to obey safety regulation. Because if the ship is overloaded, there will be danger to the seamen on the crew. Okay, so they adjust themselves the number of load that they are putting, and if the danger occurs, then they can do something by perhaps throwing things off the sea, okay, to make it lighter, or avoid going to places where they will sink even more. Or in the first place, they control the amount of load or passengers onto the ship itself.